So picking up with chapter 4 for the second lecture. So you have another kinematic property, and it analyzes the flow of fluids, and it's the vorticity vector. It's defined mathematically as the curl of a velocity vector. So here is the literal curl, but here's the vorticity vector, and then the rate of the rotation vector here. And you can see that inverse here, 1/2. The vorticity is equal to twice the angular velocity of a fluid particle. So you can see why this is over 2 here when you're going to the rate of the rotation vector, because it's equal to twice the angular velocity of a fluid particle. So here you have the angular velocity, and then you have double that for the vorticity vector. So here down where the hand is, the direction of a vector cross product is determined by the right-hand rule. And so here, when putting your right hand in this area, so thumb outstretched pointing up, and then your pointer outstretched pointing straight, and then your ring or middle finger is tangent to your pointer finger. And so the heel of the right hand is placed at the point where 2 tails of the vector are connected, and the fingers of the right hand then wrap in a direction from A to B. When this is done, the thumb of the right hand will point in the direction of the cross point C. So it makes that, that C for A times B. Okay, if the vorticity at a point in a flow field is non-zero, so if the vorticity at a point is non-zero, the fluid particle that happens to occupy that point in space is rotating, and therefore it is rotational, right? So if it's non-zero in a flow field, if it's non-zero, it is rotational. Okay, likewise, if it is 0 or negligibly small, it is irrotational. Physically, flow particles in a rotational field of flow rotate end over end as they move along the flow. So they just make a circle, like a cyclic. You can see it going from here, completing. Okay, and then you can see irrotational, where the actual particle is staying the same. Vorticity vector in the Cartesian coordinates, and so that's just an integration there, and then as well as the 2-dimensional flow in Cartesian coordinates. And then you can see this rotation also. Okay, here's a contour plot of the vorticity field due to the flow impinging on a block. As produced by CFD calculations, only the upper half is shown due to symmetry. Okay, so this is a symmetry plane, which means everything here is going to be equal but opposite. The blue regions represent large negative vorticity. So this is the negative vorticity region, and the red regions represent a large positive vorticity region here. And then the rotationality in a 2-dimensional flow. So it's steady, a steady, incompressible 2-dimensional velocity field. And it's found by here, and then as well as the vorticity. And so deformation at the initial square fluid, you can see these a lot better when they are visually constructed from those calculations using a CFD analysis, or just on an XY plane is just extremely helpful because you can see the deformation, right? So here it's for a time period of 0.25 and then 0.50, And you can see the several streamlines in the first quadrant, and it's clear that the flow is rotational. And so that's because look at the deformation, right? So deformation at an initially square fluid particle is subject to the velocity field, and therefore we have some rotation going, right? So this point is now to here, 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 right? So it's rotating, it's deforming. And then here, the vorticity vector in a cylindrical coordinates, and then two-dimensional flow in the same coordinates. And you can see here, and then another straight through here. So for two dimensions flow in an RO plane, the vorticity vector always points to the Z or in the Z direction. In this illustration, the flag-shaped fluid particle rotates in a clockwise direction as it moves into the RU plane. Its vorticity points in the Z direction are shown, so you can see here. So let's look at a comparison of two circular flows. We have flow A, and then flow B. And here, streamlines are velocity profiles for A, which is solid body rotation, and B, which is a line vortex. And then flow A is rotational, but flow B is irrotational everywhere except at the origin. Okay? So this is, and you can see by the smiley faces that it's clearly rotational. And then you can see by the smiley faces in flow B that it is not rotational aside from at the origin. Okay? And so here, if we look at flow A, UR is equal to 0 here. And then U theta, which is up here, is equal to omega R. So as you can see, we're rotating. We are rotating. And then when we get to here, we don't get into anything. And so then when we look at flow B, which is line vortex, you have UR is also equal to 0, so we don't have any rotation here. And then U theta is equal to K over R. And so you can see that here. Okay, and then flow A is solid body rotation. And you can see this as 2 omega K. And that's because it's twice the length. And then when we talk about flow B, the line vortex, that's going to be equal to 0 because the vorticity vector is not moving, it's non-rotational. So here's a simple analogy. A rotational circle flow is analogous to a roundabout, where irrotational circle flow is analogous to a Ferris wheel. So you can see this is going around kind of on, I like to say normal 2. Oh, it just deleted. So this rotation, I feel, is normal to the ground. Okay, and so here, as children revolve around the roundabout, they also rotate on the same angular velocity as the ride itself, and that's the rotational flow. But when you're talking about a Ferris wheel that's more end over end, they always remain oriented and upright, and they trace out their circular path. So that is an irrotational flow. So here's a formula for a line sink. Basically, a line sink is a point or a single point that is a determined amount of length deep at which the flow disappears. And so this shows it in reference to streamlines, and then streamlines in the R theta plane for the case of a line sink. So you can see that you can see the streamlines are coming in here. So these are our streamlines, these are our flows, and then that line sink is going off of one streamline on an XY coordinate And at that point is when the flow disappears. So the Reynolds transport theorem, we did talk about this quite a lot when we were talking about the material derivative and how we use that Reynolds transport theorem to take our system or what we are looking at and then flow it through a control volume and analyze that. So you can also look at it as the two methods of analyzing spraying of deodorant from a spray can. So you see we have a system, and you see you have two versions, like you have what's in the can and then the spray mass that is exiting the can. And then here A, if you look at picture A, we follow the fluid as it moves and deforms. This is the system approach, right? No mass crosses the boundary and the total mass of the system remains fixed. And then B, we consider a fixed interior of the can, and this is the control volume approach. And that's the mass crosses the boundary. Okay? And so here, just a little note, the relationship between the time rates of change and the extensive property for the system. The control volume is expressed by RTT, the Reynolds transport theorem. And so here, this is kind of what I drew earlier, where we talked about you have this system or, this flowing gas, and you're pushing it through or between the system approach and the control volume. And you can marry those two by the RTT. Okay, so here, the time rate of change of property B of the system is equal to the time rate of change of B of the control volume plus the net flux of B. So remember, we walked through these, through that sounds very familiar to the adjective term. This equation applies at any instance in time where it is assumed that the system and control volume occupy the same space in particular instance in time. So here we have in red, we have this control volume. It remains fixed. That's what we're looking at, right? That's our control volume. And then the system plus time is here. It's T plus the change in T. And then the system, which is the material volume and control volume at the same time. So that's that green region. It's all shaded. And then you see the inflow and the outflow. So if you can imagine, you see this velocity, this flow coming in and going out. So the system that we're looking at is just at that point, right? Because there's going to be a constant material volume in this shaded region. It may be different particles depending on, if you're looking at it a change of time apart, right? But you're taking kind of like an instantaneous snapshot of it. And then you are looking within your control volume at whatever material is in there. And then you can see that this material now changes for the system at a time, which is the hatched region. And you see how it's moving. So a moving system here is a fixed control volume in a diverging portion of the flow field at times, the upper and lower bounds of the streamline of the flow. So it's just basically what it's saying is that your system is moving like within the lens of this camera, because this is what you're looking at, the red portion. So here is some formulas for let B represent any extensive property, mass, energy, momentum, and then let B over M represent the corresponding intensive property. And then you have the formulas here for control volume and time and change in time. And then you can subtract it. And basically all of this information is just so that you can get these two formulas. It's just the background information. And since this and this, then we can get this. And so here's the control volume. So this is I think a better image. So this red line, that's kind of like the frame or the lens of what you're able to look at, what you are observing. And the control volume is whatever mass is occupying that at one time. Okay, so you'll have mass entering, mass leaving in all different directions, right? So the integral of B rho V and N, dA, all of that, over the control surface gives the net amount of property B flowing out of the control volume into the control volume is negative per unit time. So it's giving you the amount of it. And if it's into the control volume, it's negative. Okay? So out is positive and into is negative. Okay, here's outflows and inflows, right? So if theta is less than 90 degrees, then cosine theta is greater than 0. If theta is greater than 90 degrees, cosine theta is less than 0. And if theta is equal to 90 degrees, then cosine theta is equal to 0, which is no flow. And so that's where you can see this outflow and inflow here. And then here's additional formulas. Again, we're not going to spend a ton of time on this because we're going to be working the problems. Here's relative velocity, RTT, non-fixed CV, and then RTT at a steady flow rate. So here we're taking the absolute reference frame. So we have the same control volume for both, but absolute versus relative takes into account the velocity of the car. So this one is including, and this is reducing the velocity of the car. And this is the RTT applied at a control volume moving at a constant velocity. Here's more additional information, an approximate RTT for well-defined inlets and outlets. And this would be for each individual outlet or each individual inlet if you had multiples within the system, just like this. And so here we have a control volume in which one well-defined inlet here and two well-defined outlets. So you would have both of those formulas for each one and use a subscript 2 and 3 for each of those. In such cases, the control surface integral in the RTT can be more conveniently written in terms of the average values of fluid properties crossing each inlet and outlet to make the calculations not so cumbersome. Here's the one-dimensional Leibniz theorem. Okay. And it's an alternative to the RTT. And so they describe it as a more elegant mathematical deviation from RTT. And it does take into account the changes in limits. So A and T here with respect to time, as well as the unsteady changes of the integrand GXT with time. So here it is shown on a one-dimensional, and it's required when calculating the time derivative of an integral with respect to x. And they do have it in three-dimensional as well, and it's for a volume integrand. And so here, if we apply the Leibniz theorem to special cases of a material volume, a system of fixed identity moving with a flow, everywhere on the material surface, since it moves with the fluid, here V is the local fluid velocity, and then from that you get this formula for the material volume if you wanted to know how this was discovered and manipulated. Here it is seeing a three-dimensional with that control volume as well. And then this is the general RTT, a non-fixed control volume. So this is the system and the control volume at a time. So this, you see it's a change. So this thicker line is the original one, and then we have a change in time. And then we have a different direction flow here with a system at time. And then the Lagrangian description and the Eulerian description, and then how these are connected with system analysis and then the control volume analysis using the RTT. And so here we have, this is the material derivative. That looks terrible. Let's see. Material derivative, and then a RTT. And this is how we connect those. And so these are the summaries that we went over. We will go into more detail about certain portions of this. This PowerPoint and chapter was very large, so this PowerPoint is really just to introduce you to some of the verbiage that we'll use. And here's a short video to help summarize the entire chapter.
Fluid properties are usually treated as continuous functions of position in a flow field, since their variations are quite uniform. For example, we don't usually think of flowing honey as being composed of individual molecules. This differs from the approach of basic kinematics, where the trajectories of individual particles or systems are studied. To analyze fluid mechanics problems, we most often use an Eulerian frame of reference, where we observe a fixed flow field rather than following individual moving fluid elements. In this Eulerian method, we study the properties of the flow pattern in terms of spatial position and time. In a few cases, it's more useful to follow a specific fluid mass through a flow field using a Lagrangian reference frame attached to the mass. Here, the blob of white water is followed as it moves downstream. But if we mark the instantaneous boundary of the blob of fixed mass at a certain time, then we can watch the water flow through this boundary while the original white blob flows on. This is the Eulerian approach. The Lagrangian approach works best, for example, in meteorology, where a weather balloon drifts along with the prevailing wind. This reference frame is inferior to the Eulerian approach, however, in treating the airflow through a jet engine. In this case, a control volume is fixed to the jet engine with air flowing through it. Likewise, an appropriate Eulerian control volume for this hairdryer is fixed to the dryer itself rather than to the air passing through it. In this simple example, the control volume has one inlet and one outlet, and its lateral sides are impermeable to the air. Electrical energy enters the control volume, however, in order to heat the air and drive the blower that moves it. The fundamental conservation laws, such as Newton's second law of motion, were originally written for a system of fixed mass, in other words, using a Lagrangian approach. In order to apply the more useful Eulerian framework in fluid mechanics, we need a mathematical way to translate between the two frames of reference. This is Reynolds' transport theorem, which makes use of the so-called material derivative. The rate of change of a property in a fixed mass system is given as the time rate of change of that property inside the control volume plus an advective term describing the net flux of that property through the control surfaces. Here's a high-speed visualization of gas emerging from an aerosol can. We could try to follow the gas as a system of fixed mass, but the phenomenon is easier to analyze if we draw our control volume around the can and treat the gas as an advective flux through the control surface. In all of these flows, it's important to appreciate the visual flow patterns as well as the mathematical analysis. There are four basic types of flow lines that we need to understand in order to interpret these patterns: streamlines, streak lines, path lines, and timelines. The streamlines are instantaneous lines of the flow, while the streak line, path line, and timeline are generated over the passage of time. A streamline is a line everywhere tangent to the velocity vector at a given instant. The streamline comes directly from the mathematics of the flow, while the other three types of lines are often generated experimentally. Here are the streamlines for a flat plate fixed at a certain angle in a smoke tunnel flow field. These were measured by particle image velocimetry, or PIV, a modern tool of experimental fluid dynamics. A streak line is the locus of particles which have earlier passed through a prescribed point. It can be produced experimentally by the continuous injection of tracer particles at a given point in the flow. A path line is the actual Lagrangian path traversed by a given fluid particle. It can be observed in a time exposure of a single marked particle moving through the flow. In steady flows, streamlines, path lines, and streak lines are identical. A timeline is rather different. It is a line of fluid particles across the flow at a given instant, and it reveals the velocity profile. In unsteady flows, streamlines, streak lines, and path lines can be quite different. Here, the unsteady flow over a rotating plate is shown. When the flow is observed at an instant when the plate angle is the same as in the previous steady flow, we can see that all three lines differ. The streak lines and path lines, which developed over a time history while the plate was rotating, differ from the instantaneous streamlines. To understand fluid flows, we must first see them. Flow visualization is the science and art of observing fluid flows that are normally invisible. It should come first in any fluid dynamic investigation, since it provides us with an overall physical picture of the flow phenomena. Detailed measurements of quantities like pressure, temperature, and velocity are not likely to be understandable without such an overall picture in mind. Some flows are visible to the human eye without any assistance. For example, here we can see the evaporative phenomenon called wine tears merely by looking at a glass of wine with appropriate illumination. Differences in surface tension cause the wine to stream down the sides of the glass. Another example requiring only simple illumination to visualize the flow is the hydraulic jump caused by the stream of water in a kitchen sink. The hydraulic jump represents an abrupt change from so-called supercritical to subcritical flow. Here we observe the mixing of red and white paint stirred by a paddle. The flow is self-visualizing because the paint pigments reflect different colors of the incident white light. Eventually, given enough stirring, the two pigments become well mixed on a molecular scale, and we observe an intermediate pink hue. Similar mixing can be visualized in a computational fluid dynamics, or CFD simulation, by marking a blob of fluid particles red and following the distortion of the blob. For visibility, the red pigment is shown mixing with a transparent fluid. Here's a much more complicated self-visualizing flow. A white-hot jet of plasma melts its way through a steel plate. Surface tension effects determine how the molten metal accumulates on the bottom of the plate shown here. This flow appears to be undergoing some sort of periodic process. One of the simplest of flow visualization techniques involves the motion of an oil film on a surface. Here's a compressed air nozzle aimed perpendicular to a flat white surface. This flow is invisible without the assistance of a flow visualization technique. By placing droplets of colored oil on the surface, we can observe streaking caused by the shear stress of the impinging air jet. This is a simple example of the oil flow technique, a method of surface flow visualization. It gets a little more complicated when the jet impingement is not symmetric. Here the jet comes in at a 45-degree angle from the left. This technique is very useful in wind tunnel testing of aircraft models. It only indicates the flow direction very near the surface, but it's quite easy to use. Of all the different flow visualization techniques, we most often add particles to a flow to make it visible. The particles scatter light, as in this plume of smoke from a cigarette. Without the smoke particles, the plume would be invisible. In another example, particles of talcum powder were spread on a surface, and a dog was encouraged to sniff a treat lying there. From this, we see that the air exhaled by the dog's nose disturbs the talcum particles, and the subsequent airflow pattern is revealed. Here, the air surrounding a person is seeded with theatrical fog. When the person takes a walk, the fog indicates the airflow in his wake. A vertical sheet of laser light is used to illuminate a plane in the center of this complicated turbulent flow, known as the human aerodynamic wake. Next, a paint spray gun is aimed perpendicular to a sheet of plywood that appears edge-on in the video. Once again, laser sheet illumination reveals the paint particles. In this unsteady flow, the spray strikes the plywood, but not all of the paint is deposited. Some of the smaller particles escape, in what is known as a starting wall jet. These overspray particles are a problem. They must be captured, or else they will cause air pollution. Another major category of flow visualization is optical methods. Typically, a beam of light is passed through the flow, and parts of the beam are refracted due to flow disturbances. The disturbance in this case is the heat shed by the human body, which creates a warm, turbulent plume, the human thermal plume. The subject is standing in front of a precise parabolic telescope mirror 1 meter in diameter, big enough to be the centerpiece of an astronomical observatory. Instead, it's actually the centerpiece of a Schlieren optical system, a laboratory technique for visualizing density differences in transparent media. Considering the human body as a heat engine, most of the calories we consume are rejected as waste heat, which is shed by thermal convection and radiation. Without the human thermal plume, our bodies would overheat with dire consequences. In addition to the particle seeding technique shown earlier, the Schlieren technique can also reveal the airflow from a dog's nose. The inhaled air is at room temperature and is not visible, but the exhaled air has been warmed inside the nose. We can see that it forms jets from the dog's nostrils that are aimed downward rather than straight ahead. A special Schlieren system is used to visualize very large flow fields. Here we see thermal plumes rising from a person and a computer. This warm air is removed at the ceiling, while the air conditioner on the left emits cool air that falls to the floor in a scheme known as displacement ventilation. We can use the same approach to study ventilation in commercial kitchens, where the heat and fumes from a griddle are collected overhead by a ventilation hood. The Schlieren method is especially useful to visualize high-speed flows in wind tunnels. Here we see Mach 3 airflow starting and stopping over a wedge-shaped model in a supersonic wind tunnel. Finally, some flows happen too fast to be observed properly by the human eye. High-speed imaging is required to slow these flows down. This milk splash requires no special visualization technique other than slowing it down by a factor of 33 using a high-speed camera. This Schlieren video of a supersonic air jet from a nozzle is shot at the usual rate of 30 frames per second, but each frame is exposed for only 1 microsecond. This is a kind of pseudo-high-speed imaging that reveals the radiation of jet noise from the flow. The shedding of a Kármán vortex street from a cylinder is graphically visualized in a soap film tunnel. However, the vortices happen too fast for direct observation, so a high-speed camera slows the flow down by a factor of 15. This phenomenon of Kármán vortex street shedding can also be predicted numerically using CFD, as shown in this computer animation. The motion of vapor bubbles in nucleate boiling is likewise too fast to follow with the eye, so the high-speed camera allows us to observe it at a convenient speed. These flow visualization techniques and others allow us to study and understand the kinematics of fluid flows.